I want you guys working on questions 9 and 10 right now. They're both pulley questions, system questions. Okay, number 9 has to do with this diagram on the right, okay, and number 10 has to do with this pulley diagram here on the left. So one is a vertical pulley, okay, and the other is a pulley system with one mast sitting on a table. All right, so I want you guys working on those two questions for right now, and then we'll walk through them here in a few minutes. All right, so with number 9 here, guys, okay, we got two blocks and they're set up like that. Okay, the forces involved here, okay, are the force of gravity acting on mass 1 and the force of friction acting on mass 2. Okay, those are the forces that are involved. There isn't anything else. It says the pulley is frictionless, so we don't have to worry about that. Okay, actually it doesn't say that, but we have to assume it. So mass 1 is 6 kilograms. So to calculate the force of gravity, we're going to go m times g, and we're going to get 58.78. Is that right? 58.86. All right, 58.86 newtons, okay, is what we've got for the force of gravity there, and they told us that the force of friction is 4.0 newtons. All right, so now that we have that, I simplify my free body diagram. This system has a mass of 10.5 kilograms, okay? It is being pulled this way by 58.86 newtons worth of force, okay, and it is being resisted this way by only 4 newtons of force, okay, so I can calculate the net force right away here. So F net will be 58.86 minus 4, which will be 54.86 newtons. All right, so there's my net force acting on the system, and then to calculate the acceleration of mass 1, I have to calculate the acceleration of the system, all the mass, okay? 54.84 divided by 10.5 kilograms. All right, so that's going to get us 5.2 meters per second squared, and I have to put a vector on, or sorry, it's mass 1, so I have to put a vector of down on that. All right, so that would be our answer there. Ryan, question? Oh, sorry, it's supposed to be 8.6. Just me not paying attention. Not enough coffee yet. All right, any other questions besides point out Coderre's an idiot and screw up the numbers? All right, how many people have done number 10? All right, I'm going to give you a few more minutes on 10, and then I'm going to go over it as well. Okay, so on number 10, we have a vertical pulley, similar, really there's not a whole lot different in a vertical pulley to what we just did with the pulley with a mass on a table. Okay, we're still dealing with a system where we have to combine the masses. Okay, so the forces are the force of gravity and the force of gravity. Okay, those are our two forces here. Okay, so mass A is 10 kilograms and mass B is 18 kilograms. So the force of gravity on mass B will be 18 times 9.81. All right, so we're looking at 176.58 newtons there, and then this is obviously 98.1 newtons here. All right, so we've got our two forces. Then we can simplify the free body diagram to be 28 kilograms being pulled this way by 176.58 and this way by 98.1. Calculate our net force. Okay, so 176 minus 98.1 should be 78.48. Yeah. Newtons. Okay, then I calculate my acceleration. Okay, F net over m. Okay, what mass do I use? Yeah, I use 28, the whole mass of the system. So 78.48 divided by 28. Okay, and that'll give me my 2.8 meters per second squared, and that needs to have a vector of up on it because that one is definitely moving upwards. Okay, are you starting to make some sense? All right. All right, so yesterday we did some Newton's third law stuff. These are way easier than the box A pushes on box B pushes on box C questions. Okay, they're still Newton's third law questions, but they're basically one thing pushes on one thing. All right, so they're quite a bit easier. So I'd like you guys to try those Newton's third law questions. There's only 4 of them there. Okay, I think you'll get them done pretty quickly, and then we'll go through them. All right, so for number 4 here, so we're standing on a horizontal frictionless surface, and a 45-kilogram student throws a 3-kilogram object to her right. Okay, during the throw, the object was accelerated horizontally through a distance of 0.6 meters from rest to a velocity of 9.6 meters per second. Calculate the velocity of the student when the object is released. Okay, so here's what we need to know first off, is that the force on the student is equal to negative the force on the rock. Everybody okay with that? Right, there's a rock, right? Yeah. All right, so it just says an object. All right, FO, object. All right, that means that the mass of the student times the acceleration of the student equals negative mass of the object times the acceleration of the object. Agreed? All right, can I use this to figure out the acceleration of the student? Yes, I can. That's my first step. Knowing that these forces are equal helps me to calculate one more piece of information about the student. The student was also initially at rest. Okay, so this is information about the student. VI is 0 meters per second. Okay, the distance for both the student and the object is the same. Okay, everybody with me there? The distance that she pushes the object has to be the same as the distance that she's going. All right, and then I'll have the acceleration here in a minute. All right with that? Okay, and that's all that they tell us there. We could also calculate the time if we wanted to, and that might even be more accurate than saying the distance is the same, but we'll go with it from here. Okay, so I'm going to calculate the acceleration of the object here. Okay, so the acceleration of the object, I have VI, I have VF, and I have D. All right, so I'm going to use VF squared minus VI squared over 2D and get the acceleration of the object. Okay, so that'll be 0 squared minus 9.6 squared divided by 2 times 0.6. Right, it was 0.6, yeah. All right, so the acceleration of the object is 9.6 squared divided by 1.2. All right, so the acceleration of the object is 76.8 meters per second squared. Okay, it's big, but it's small. Okay, the mass is small. Its acceleration is big, its mass is small. All right, now that I have that, I should be able to calculate the acceleration of the student. So that's what I'm going to do here. The acceleration of the student is going to be the force on the object divided by the mass of the student, because the forces are the same. All right, so I'm going to take that 76.8 and multiply it by 3. Okay, that gives me the force. All right, then I'm going to divide that by the mass of the student. All right, so the acceleration of the student is 5.12 meters per second squared. All right, so now I have 5.12 meters per second squared. Okay, so now if I use the same formula, I should be able to get their final velocity. And if that doesn't work, then I'll try it with the time, but okay, it should work. So we've got 2 times 5.12 times 0.6. Oh. And then I got to square root that. Okay, that's not right. Oh, I wrote 6. Okay, 2 times 5.12 times 0.6. Okay, and then square root that. Okay. Oh, no, it didn't work. Oh, no, the distance wouldn't be the same. What am I saying? Their acceleration is less. Their distance would be less. Sorry. I don't know what I'm thinking there. Okay, so what we have to do is calculate the time. Okay, we got to calculate the time. Sorry, I don't know why I said that. That's dumb. Okay, so we got to calculate the time of the acceleration. The time is the same for both. That's what I was thinking, and I said distance. And then I kept going with it. That's dumb. I need more coffee. Okay. All right. So we got to calculate the time. Once we have all this information here, we can calculate the time using the object quite easily because we have VI, we have VF, and we have A. All right. So I'm going to go VF, which was 9.6 minus 0 divided by 76.8 meters per second squared. Okay. So sorry, 9.6 divided by 0.8, so it's a very small time because it doesn't take you long to throw something, right? So 0.125 or an eighth of a second. Then we can bring that over here, and we're not going to use this formula. Okay, now we're going to use this formula. We're going to go with VF equals A times T plus VI. Right? And VI is 0. Right? So we're just going to go 5.12 times 0.125, and that should give us 0.64. There we go. That's what I used. That's what I used. VF minus VI over A. That's what I did. That's what I did. VI was 0. So I just went A times T. Yeah? So yes, I can. And I did. No, not in this formula. It's A equals VF minus VI over T. I just manipulated for VF. Right? It's not squared there. Okay. All right. So that's a tricky one. It's not so much tricky, it's just there's a lot of finicky math in that one as opposed to it being overly tricky, although it tricked me because I wasn't paying attention. Happened to anybody. All right. Are we feeling pretty good about the Newton's third law stuff? Okay. Like on the unit exam, I've occasionally had a Newton's third law problem in the written response, but I don't always. But I often have stuff in the multiple choice about Newton's third law, simple calculations, okay, where the force would be equal or something like that, or understanding type questions. Okay, we talked about the smart car versus the semi truck, right? And we said the forces are the same, but the accelerations are different because the masses are different. It's Newton's third law. The forces are equal. Okay, if I hit a wall, the wall hits me back. Okay, same amount of force, right? Opposite direction, but accelerations are different. Okay. Last couple of Newton's second law problems that I want you guys to work on here were okay, I wanted you guys to do number 8 because that one was an inclined plane with coefficient of friction. So, because we haven't done that one yet, right? All right. Okay, so I want you guys to do 7 and 8. Okay, so they're both inclined planes, but number 8 involves using the coefficient of friction on an incline, and we haven't done a lot of ones like that. Okay, so 7 and 8 for right now. All right, so let's quickly look at 7 here. So we got a kid who's log rolling, okay, down a 10-degree incline. Okay, the child has a mass of 20 kilograms. Okay, and friction is opposing with 2.5 newtons. So if they're log rolling down, friction is moving up. Okay, we're looking for the acceleration of the child. What's the force pulling them down? F parallel. All right, so what I have to do here is calculate my internal triangle, same as always. So this will be 196.2. Okay, I don't need F normal for this question. Right, F parallel is here. Okay, this is a 10-degree angle. So I'm going to go sine of 10 degrees times 196.2, right, which gives me 34.07 newtons down. Okay, then I just calculate my net force. So I subtract from that the 2.5 newtons of friction. There's my net force. I divide that by the mass of the child, 20 kilograms. And I've got my acceleration, 1.6 meters per second squared down the hill. That's the wrong significant digits because I used that force. Okay, everybody with me on that one? Okay. How many people are done 8 again? Okay. Let's have a look at 8. So with a ski jumper, okay, we're going down a 35-degree ramp. Okay, 70 kilograms. Okay, obviously F parallel is pulling down the ramp. Friction is pulling up the ramp. I don't know the magnitude of either one of those. I'm going to have to calculate them both. All right, calculating F parallel, same as always. Okay, so this is FG. 686.7 newtons for the force of gravity. This side is F normal, and I'm going to need it. Okay, and this side is F parallel. I'm also going to need that. All right, so this is a 35-degree angle. So I'll calculate F parallel first, same as we always do. Sine of 35 times the weight, 686.7. All right, so we've got 393.87 newtons acting down the ramp. Now, if I'm going to calculate the force of friction, then I have to use this formula, mu times the normal force, which means I've got to calculate the normal force. Normal force is the adjacent side, so that'll be the cos of 35 degrees times 686.7. All right, so 562.51. So this is the step we haven't done very much. 562.5. Okay, so if we're given the coefficient of friction on an inclined plane, that's when we need to calculate the normal force. It's the only inclined plane situation where normal force will be important to actually have as a number. All right, so now that I have that, now I can plug it in here, okay, because we know the coefficient of friction was 0.120, okay, times the normal force that we just calculated. So I'm going to go times 0.12, and there's my force of friction, 67.5 newtons. Now it's the same as every other Newton's second law problem. F parallel plus the force of friction. So it's sum of all forces. Okay, so we take our 393.8749,388 and subtract our answer, which was the force of friction. Okay, there's our force parallel, or sorry, our net force down the ramp. Divide that by the mass of the skier. So there's our m times a calculation. Acceleration down is 4.66 meters per second squared down the hill. Okay, I don't have a vector on mine, and I should. It should say down the hill. All right, is that making some sense? All right, how are we feeling about Newton's second law? I'm feeling fairly confident because you've seen now quite a few different examples. You've seen static examples where, like the hanging signs. Okay, we've seen all kinds of vector-related ones like hanging signs and things that are pulled at an angle, like the box pulled along the table by an angled force. Okay, we've done a bunch of inclined planes. Okay, we've looked at box pushes box kind of questions, systems, pulleys, all that kind of stuff. Okay, you have a pretty good idea now of most of the situations you can run into. Obviously, there's ways I can take those situations and spin them, but at least now you have the background on those. So on Monday, you're going to get your assignment on Newton's second law. Okay, I will give it to you, and I will let you have the class to work on it. Okay, the entire class to work on it. So you should be able to get it pretty much done. Okay, if you stay focused on it. Tuesday, doing a lab on friction. Okay, and then Wednesday, we're going to start work energy theorem, which is like this last third of the unit. Okay, good news is that's all pretty much the same as what you learned in Science 10. Right? The only thing we change is instead of only changing one type of energy, both types of energy can change at the same time. It's not really any more difficult. All right, so that'll be the plan going forward. Okay, remember that if your parents have booked an interview with me for this afternoon, you should come along. Okay, any questions on any of this stuff? All right, then we're going to call it.